What's up everybody, my name's Eric Leffler and this is the Engineer Project. In this video I'm going to discuss internal combustion engines. We're going to start with the 4-stroke internal combustion engine typically found in vehicles and move on to natural gas turbines found in power plants. And then we'll discuss the similarities to Nikola Tesla's turbine by reviewing a few of his patents. At the end of this video, I'll explain how I intend to build a Tesla turbine on steroids. This is a cutaway sketch of a single cylinder of a 4-stroke engine typically found in vehicles. The first thing you may notice is that there's a lot of moving components. The crankshaft, connecting rods, piston, intake valve, exhaust valve, camshafts above those valves are all moving components. The engines are called 4-stroke engines because the piston has to make 4 strokes to complete a cycle. The first stroke is the intake stroke. With the piston at the top of the cylinder beginning to move downward, the intake valve opens, allowing an air-fuel mixture to rush into the cylinder. The downward travel of the piston sucks the air-fuel mixture in, and when the piston gets to the bottom of the cylinder, the intake valve closes. The second stroke begins when the piston begins to rise with both valves closed, compressing the air-fuel mixture. When the piston gets right to the top of the cylinder, an electric current passes through the spark plug, causing a spark that ignites that air-fuel mixture under a whole lot of pressure. This ignition causes a small explosion, and the rapid expansion of all that burning air and fuel forces the piston back down in the cylinder, and this is called the power stroke, where all the rotational energy comes from. When the piston's at the bottom of the cylinder, the exhaust valve opens and the engine begins its final stroke, rising back up and pushing all the spent combustion gases out of the exhaust. And that process repeats itself over and over and over again. So, something to note on top of the quantity of moving components is that only one stroke makes useful energy. The power stroke is not only providing power that the engine makes, it's constantly robbed of power to operate the other 3 strokes. The intake and exhaust strokes are pretty low resistance, but the compression stroke sees quite a bit. In this cutaway video of a natural gas turbine, we can get an idea of the similarities to a 4-stroke internal combustion engine found in vehicles. On the right side in purple, we have our intake similar to the intake stroke of a 4-stroke engine, except there are really no moving components related to taking air in as the turbines open to the atmosphere. Once air begins entering the fan blades though, the air begins to compress, kind of like the compression stroke of a 4-stroke engine. The fan blades are exerting force on the air and that causes this compression as they go from stage to stage. Fuel is added midway through the turbine and the air-fuel mixture is ignited and combusted. Once again, the combustion of the air-fuel mixture exerts force against the power side of the turbine fan fins, creating rotational energy similar to the power stroke of the 4-stroke engine, and all the spent air-fuel mixture is exhausted out of the back. In a combined cycle power plant, the exhaust of this turbine would be connected to a heat recovery steam generator. Much like the 4-stroke engine, this engine is losing power to the compressor blades to compress the incoming air. There are quite a few more moving parts, but there are far fewer moving components. Unlike the 4-stroke engine found in automotive vehicles, natural gas turbines provide continuous operation. Now let's look at the Tesla turbine. This is British patent 24001. I like it because it shows the turbine as a centrifugal pump and reversible turbine configuration as well. Much like a natural gas turbine, there is only one moving component, the rotor, consisting of the shaft and multiple flat discs. Nikola Tesla's most basic internal combustion engine patent we find is actually part of his valvular conduit patent, 1329559. We can see in figure 4, Tesla planned to use these valvular conduits as intake valves for air and fuel to be fed into a combustion chamber right on top of the turbine. This is a very interesting concept. There would be no work lost compressing air, which both other types of internal combustion engines have to do, and there are very few moving components. Heat may become an issue, but with modern metallurgy technology, there may be a solution for a really simple turbine by just copying this design. When we evaluate Tesla patent 186083, there is a lot going on. Many people have said that Tesla was ahead of his time, and I find the similarities in this patent to modern combined cycle power plants very intriguing. This design was intended to be used to increase the efficiency of steam power plants and assumes steam on site. Steam enters through valve 7 and distributes it to both sides of a turbine. Inside of number 14 and the cutaway version number 15, we have combustion chambers. The steam and exhaust enter the combustion chambers together, causing the turbine to rotate. This turbine is basically an internal combustion engine and external combustion engine hybrid with both types of engines we find in a combined cycle power plant in one turbine. What else do we find in combined cycle power plants? A boiler known as a heat recovery steam generator. Well, conveniently, on this design, he has a boiler as well. We have talked about both four-stroke and natural gas turbine engines having to compress air as part of their operation. In this patent, Tesla has a compressor to feed pressurized air into the combustion chambers. In cars, you may have heard of turbochargers being used to increase efficiency in our vehicles. These are installed in the exhaust pipes of vehicles, and the exhaust gases spin the turbine wheel, which is connected to a compressor, much like these big turbines, but just little bitty guys. That will make sense in a minute, so I'm going to come back to it. I'm going to go a little bit more off base here and show you a multi-stage pump like I used to work on as a design engineer. This is a Flowserve axially split multi-stage called a DMX. Fluid enters here on the right and goes into the second and third impellers. Then the fluid crosses over to the fourth stage on the opposite side of the pump and with the impellers flipped in the opposite direction, and then the fluid flows through into stages 5 and 6 and discharges in the middle of the pump on the backside, which we can't see in this view. The main thing I want you to take away from this is simply having multiple impellers on the same shaft. With all of this in mind, I hope you followed along so far because I'm going to tell you now how I think all of this goes together in a way that would create a hybrid engine that is an internal combustion engine and an external combustion engine in one. I'm going to apply the concepts of heat recovery steam generators found in combined cycle power plants and turbochargers to create an engine I believe will allow me to hit that fuel mileage goal. While I like the idea of Tesla's internal combustion turbine featured in his valvular conduit design, I think there may be some issues that will make that design difficult to complete. And we've gotten quite a bit of technology since he designed all this stuff in the early 1900s. The closest design to what I think can be built is something along the lines of 186083. Let's start out by overlaying the components up here. Instead of a boiler, let's think of this as a heat recovery steam generator. Tesla feeds his combustion chamber with compressed air, so let's put a turbocharger over here for a compressor. Now we have an idea of how some modern components fit into this picture. I have concerns about combining combusted fuel and steam that would require us to exhaust steam into our atmosphere and therefore increasing our fresh water consumption. So I want to think of this in a pump style and imagine it more like a two-stage pump, one for internal combustion engine process and another for an external combustion engine process. The internal combustion engine will exhaust into a heat recovery steam generator, and then the heat recovery steam generator will operate the external combustion engine through its own cycle. I'll come back to the heat recovery steam generator in a little bit because we're going to break these up. A natural gas turbine makes the compressor part of the rotor. A turbocharger is a turbine and compressor, and we already have a turbine, so let's just take the compressor side of the turbocharger and stick it on the end of our Tesla turbine. When it comes to the combustion chamber, I stumbled over a video by Nighthawk and Light on YouTube where he was demonstrating the Tesla valve. He had a cool concept to put propane bottles in one end, blow some propane into the valve, and ignite it. Something that happened that may be useful to this design is that the flame accelerated inside of the valve. I think that by putting the combustion chamber between two Tesla valvular conduits, we can take advantage of this phenomenon. I also think we can take a look at one more Tesla patent, 186084. This container is basically a superheater. There is a combustion chamber here and the hot exhaust gas enters into a coil and steam enters the surrounding chamber to be heated by the coils before entering the turbine. By incorporating a Tesla valve that would have a flame traveling through it and encasing that valve with a chamber, we could remove the superheater from the heat recovery steam generator and use the combustion chamber to serve this purpose in a similar way to what is indicated in this patent. Now, something people don't really think about with automotive engines is that they are already boilers. The coolant system is a boiler, but its function is to maintain the engine temperature and keep the fluid from boiling using the radiator. The cooling system on vehicles is basically a preheater or an economizer, so a possible design element we can include is a cooling system for the turbine that would replace the economizer in the heat recovery steam generator. This would allow exhaust from the internal combustion engine only have to do work on the evaporator in the boiler, which I believe would lead to the highest efficiency. The turbine would be connected to a generator of some sort, which would likely require some kind of gear reduction. This system would be tasked with charging the onboard battery of a modern electric vehicle, which also would allow the battery to be smaller because distance would no longer be a factor, saving weight as well. I fully believe I can build this, and if you'd like to support us, visit TheNJNEARProject.com. That's TheNJNEARproject.com/donate. If you are watching this on our website, I'm sure I've placed a button for donating around here somewhere. With that, I'm Eric Leffler, and this is The Engineer Project. Thanks for watching this video. What's up, everybody? My name's Eric Leffler, and this is the Internal Combustion Engine.